is a model. This is a model too. This? Yep, it's a model. The word model gets used a lot in many different contexts. Just within the context of science, models include a model of an atom or compound, an anatomical model of a human skeleton, a computer-based climate model, a physical model to simulate the flow of groundwater contaminants, and many more. In a video about research using observations from the natural world, I described my work making observations about faults and past earthquakes. The observations themselves answer questions like how long the fault is and how much movement has occurred along the fault at different points. But that's not really what my research question is. I really want to know how big the earthquakes were that happened along that fault. So I take all of those measurements and enter them into a mathematical model, an equation that can predict the magnitude of the earthquake that occurred. The equation that I use was developed based on lots and lots of measurements from recent earthquakes where the magnitude was measured along with the fault length and movement, and then scientists worked to develop a set of equations that describe the relationships between these variables. When I entered all of my measurements into the equation, the answer I got indicated that the past earthquake in the area where I was working would have been a magnitude between 7.0 and 7.3. That's pretty big. If an earthquake of similar magnitude happened today in that same area, brick buildings, including many of the historic structures in the small towns, would probably not survive the shaking. Whether or not they would is something we can test with another kind of model, a more complex computer-based model where earthquake scientists build three-dimensional representations of the Earth's crust, including all of the faults and the kind of rocks that make up the crust. Then they test different scenario earthquakes, different magnitudes that start at different places, and see how the ground responds. The resulting data, often presented as an animation, shows predictions with a range of uncertainty about how much shaking will occur and how long it will last, allowing people to figure out what type of structures might survive and what type of damage different quakes would cause. These scenarios help people plan and prepare for potential earthquakes by doing things like strengthening critical infrastructure like schools, hospitals, and bridges, and preventing development in some areas where the shaking would be the strongest. Physical models are also used in research, but they need to be more than representations of something in order to be used in experiments and to make predictions. So while a plastic model of a human skeleton is a useful learning tool, it would need to accurately recreate the strength of human bone to be used in experiments on, for example, the impact of a car crash on bones. And scientists have created models like these, for example, with extinct animals like dinosaurs to understand more about how they would stand, or the strength of their jaws, or how fast they could run. They have to make assumptions about things like muscle strength, but they base those assumptions on real living animals and biomechanics. Lots of scientists use models and modeling in virtually all disciplines. If you are using models in your research, one of the most important things to understand is what the simplifications and assumptions are, so that you can determine if those simplifications are reasonable for the questions you're asking. Models can be really powerful, but they can also be really wrong if you don't know what assumptions you are making.